Hello, welcome back to the Chemistry Explained series, part 12. In our last video in part 11, we explored the mole concept and the Avogadro's number, which is a very powerful tool for counting atoms, ions, or molecules using Avogadro's number. Today, we'll move a step further into a very practical topic in chemistry: stoichiometry of chemical reactions. You will know that chemistry is a quantitative science. As chemists are often interested in how much yield and quantities of products they are going to obtain from given amounts of reactants. Through calculations, we can determine how the masses and volumes of the reactants and products are related. The study of this quantitative relationship in chemical reactions is called stoichiometry. So stoichiometry is the relationship between the masses of reactants and products before, during, and following chemical reactions. Why is stoichiometry important? Think of a chemical reaction like a recipe. Just like a chef needs 2 eggs and 1 cup of flour and other ingredients to make a cake, a chemist uses a balanced chemical equation to know how much of each substance is needed to create another. There are different kinds of stoichiometric problems. We're going to look at 5 major ones, and we're going to use examples to illustrate them. Number 1 is mass stoichiometry. Mass volume stoichiometry, the limiting reactants, the percentage yield, and volume stoichiometry. Mass stoichiometry relates the mass of a reactant to the mass of a product using molar ratios. Let's look at an example. Question 1. How many grams of water will be produced when 8 grams of hydrogen gas reacts with excess oxygen? Remember, in solving it, the first thing you need to do is to balance the equation. Look at the equation: 2 moles of hydrogen plus 1 mole of oxygen, giving us 2 moles of water. The molar mass of hydrogen is 2 approximately. Therefore, the number of moles of hydrogen, when you use that formula, mass all over molar mass, we get 4 moles of hydrogen that reacted. So the mole ratio, from the mole ratio, you see that 2 moles of hydrogen produce 2 moles of water. So 4 moles of hydrogen obviously will produce 4 moles of water. Then what's the mass of water produced? We know that the molar mass of water is 18. So using that formula again, mass, so multiply the molar mass with the number of moles of water, which gives us 72 grams of water. Example 2 is the mass volume stoichiometry. This relates mass of a substance to volume of a gas using the molar volume at STP, standard temperature and pressure. You illustrate that with a question: what volume of oxygen gas at STP is needed to completely react with 4.6 grams of sodium? The equation there is very clear: 4 moles of sodium reacting with 1 mole of oxygen to give us 2 moles of sodium oxide. Then the molar mass of sodium is 23. The number of moles of sodium reacting, the same formula, mass all over molar mass. So 4.6 grams of sodium divided by 2 to 3 grams per mole, the molar mass of sodium, we have 0.2 mole of sodium. The mole ratio, 4 moles of sodium reacting with 1 mole of oxygen, giving us, that means 0.2 moles of sodium will react with 0.05 moles of oxygen. Then at standard temperature and pressure, the gas occupies 22.4 liters or 22.4 dm3. So we simply multiply the number of oxygen reactants 0.05 moles multiplied by 22.4, and we have 1.1 liters or dm3 of oxygen. Number 3, limiting reactant problem. This type determines which reactant is completely used up and limits the amount of the product formed. We'll illustrate with a question. If 10 grams of hydrogen reacts with 80 grams of oxygen, which reactant is limiting, and how many grams of water will be produced? Again, the equation of reaction, 2 moles of hydrogen plus 1 mole of oxygen giving us 2 moles of water. Then when we convert it to moles, we have hydrogen. You remember the mass is 10, the molar mass is 2. So when you divide that, you have 5 moles. Oxygen, the mass is 80, the molar mass is 32. When you divide it, you have 2.5 moles. So from the equation, 2 moles of hydrogen react to 1 mole of oxygen. So 5 moles of hydrogen needs 2.5 mole of oxygen to produce 2 moles of water. They are imperfect ratio, so no limiting of any reactants, of the reactants. So the moles of water produced, say 2 moles of hydrogen produce 2 moles of water. So 5 moles of hydrogen obviously will produce 5 moles of water. So the mass of water, just multiply the number of moles with the molar mass, and we'll get 90 grams of water. Number 4, the percentage yield. This compares the actual product or products obtained with the theoretical maximum yield predicted. We can illustrate that with a question. Question number 4. In an experiment, 84 grams of carbon dioxide was expected, but only 66 grams was collected. What is the percentage yield? You have the formula there. Percentage yield will be the actual yield all over theoretical yield or the expected yield, and then multiply by 100. So when you substitute into the values into the formula, you have 66 grams over 84 grams multiplied by 100, you have 78.57%. That's the percentage yield. Then we'll look at the volume stoichiometry. Know that at the same temperature and pressure, gas volumes react in simple whole number ratios. It's a known law. So illustrate this with a question. What volume of ammonia is formed when 3 liters of nitrogen reacts with hydrogen? See the equation that produces ammonia. 1 mole of nitrogen reacts with 3 moles of hydrogen to give us 2 moles of ammonia. So the mole ratio of the volumes, 1 liter of nitrogen gives 2 liters of ammonia. So simply 3 liters of nitrogen will give us 6 liters of ammonia. That's 3 times 2. You have 6 liters of ammonia. So today we have gone through a very important lesson on the stoichiometry of reactions. You have to take note of these key points. Number 1, make sure that you have a balanced equation. Very essential. Number 2, use mole ratios from the coefficients. Number 3, you convert using molar mass or the volume. Thanks for watching. Like, subscribe, and comment. Thank you.